Hey class, welcome back. We are still in chapter 11, covering chemical bonds and chemical structures. But before we go any further, I want to introduce this concept of electronegativity to you guys because it's really important for several reasons, but specifically for Lewis structures, it's important to understand what electronegativity is because a lot of times when we draw Lewis structures, the central atom isn't obvious. And so, in order to pick the correct central atom, you need to know what electronegativity is because the correct central atom is always, for the most part, the least electronegative atom. So, what is electronegativity? It is the ability of an element to attract electrons within a covalent bond. Okay? Oxygen is more electronegative than hydrogen, and I'll just write that right here. So say you have a bond that you're just looking at there's another, okay, fine, water. Here's, in the specific Lewis structure for water is, okay, right there. So if you're looking at electronegativity, or you're evaluating the electronegativity of oxygen versus hydrogen, first of all, we're looking at specifically how, we'll just zoom in right here, how this bond is affected by the electronegativity between oxygen and this hydrogen right here. So I'm just going to go ahead and tell you oxygen is more electronegative than hydrogen, which means that, on average, the shared electrons within this bond, or even this bond, are more likely to be found near the oxygen than near the hydrogen. I've already introduced this concept to you guys, right? I've already introduced the fact that we know that in water, hydrogen has this slight positive charge and oxygen has this slight negative charge because oxygen pulls the electron density closer to it, right? This is called electronegativity. Because oxygen is more electronegative, it is going to pull the electron density closer to it, okay? Leaving the hydrogen a little slightly positive and then also giving the oxygen a slight negative charge. Slight, not full-on negative charge. So this is an example of electronegativity. Oxygen's more greedy when it comes to, even though it's sharing the electrons within this bond, it's more greedy, so it's going to pull electron density closer to it. The sharing isn't equal. Hydrogen is less electronegative, so it can't fight oxygen in this matter, so it just kind of allows oxygen to hoard all the electron density closer towards it. So this is just really fast. This is a representation. This is a dot representation of electron density towards hydrogen, towards that bond between oxygen and hydrogen. And this isn't a really great graphic. It's kind of hard to see here, but long story short, the oxygen has more density, electron density around it than hydrogen. That means that the bond in between oxygen and hydrogen is not equal because there's more electron density over here than over here, okay? And so what that means is that this bond right here is polar. Okay, it's a polar bond. There's an unequal distribution of electron density within this bond, right? The oxygen atom, which is obviously getting the larger share, has a partial negative charge. This is the delta minus. Hydrogen gets the smaller share. That's a delta plus. The result of this uneven sharing of electron is called a dipole moment. Okay? So I'll put dipole moment. Which is equal to or equivalent to the separation of charge within a bond. So the bond still exists, but because the bond is polar, because there's an unequal sharing of electron density, the bond is now polar, and then the bond has a dipole moment. Covalent bonds that have a dipole moment are called polar covalent bonds. The magnitude of the dipole moment and the polarity of the bond depend on the electronegativity difference between, this is really important, between the two elements. All right, we'll talk about this later on, but let me just go ahead and just show you really quickly the electronegativity trend. So, like I said, I'll jump back into this dipole moment situation later on, but I just want you to see that there's an overall electronegativity trend when we're evaluating elements within the periodic table. As you can see here, fluorine, there's a numerical value associated with each element, all right, that I have here, and that value is its electronegativity, where 0.7 is the weakest, right, cesium, and the strongest, the most electronegative, is fluorine at 4.0. So you can see here that electronegativity increases as we go across and go up the periodic table. So as we go up and as we go across. Okay? So if you had to draw the Lewis structure for hydrogen cyanide, okay, hydrogen cyanide. And you need to know what the central atom is. First of all, we know hydrogen is H, and cyanide is going to be a C, just to let you know. It's a carbon and a nitrogen. And I wanted you to draw the Lewis structure for this. And you had to place the central atom. Well, you would have to use the electronegativity, your knowledge of the electronegativity trend, to pick the central atom. First of all, we know that hydrogen is never the central atom because hydrogen, I'm going to draw it down here, only likes to be bound to one other element because it only needs one electron. So if it only likes to be bound to one other element, it's highly unlikely this is going to be the central atom because there are two more atoms that we have to place. So we call this hydrogen is always going to be terminal. It's always going to be on the end somewhere, okay? So the question is, which one is the central atom, carbon or nitrogen? So again, you're going to use your knowledge of the electronegativity trend to sit back and say which one is least electronegative. And as you can see here, carbon has a 2.5, nitrogen has electronegativity of 3.0. Nitrogen is more electronegative than carbon, so carbon is going to be the central atom. Okay, so I haven't placed any bonds here. We can actually do we'll do the Lewis structure here in a second, but carbon is going to be the central atom. Now, let's say you don't have, obviously I'm not ever going to ask you to memorize the electronegativities, right? I'm never going to ask you to memorize carbon is 2.5 and nitrogen is 3.0, but I will ask you to understand the trend. You need to understand that as electronegativity increases as we go up and as we go across. Okay? So since carbon is more left than nitrogen, okay, carbon is going to be least electronegative. Okay, so you're going to need to memorize these trends, this trend. It's very helpful when drawing Lewis structures. So I'm going to skip back to where we were before, where we were talking about Lewis structures of polyatomic ions. I gave you guys some examples. Now we're going to talk about Lewis structures of oxoacids, okay? Oxoacids. So essentially, oxoacids are polyatomic ions with a hydrogen associated with it. Now, the big question is, well, here, I'll give you an example. So here, we have HNO3, and our polyatomic ion is our nitrate, NO3 minus, but then you'll see there's a hydrogen associated with it. Right? So it's going to give you HNO3. Another oxyacid that we would, polyatomic-wise, is H2SO4, all right? And you can see that that's, when we break it up, it's going to be two hydrogen ions and sulfate. Sorry about that. Sulfate anion. We put those together. And that's going to give you H2SO4. So these are considered oxyacids. So they're polyatomic ions with a hydrogen associated with it. Hydrogens, again, are always terminal, okay? And with these oxyacids, the big question is, where are they going to go? Yes, I just said that they were terminal, but they're always going to go on one of the oxygens, okay? They're always going to come off of one of the oxygens. So when we draw the Lewis structures for these guys, we're going to follow the same method as we had been doing before for polyatomic ions. However, the hydrogens are going to be attached to the O's in an oxyacid, not the central atom. Okay, so that's key. Not the central atom. So let me just go back up and let me just give you some examples. So we said, let's do HNO3. All right. So the first thing we have to do is we have to add up all of the valence electrons. So we have, I'm going to move this. So number one, add up the valence. Hydrogen, I'm just going from left to right. Hydrogen, 1 electron. Nitrogen, oops, why does this keep happening? Sorry about that. Let's see if I can. Nitrogen always gives you 5 valence, and then oxygen is going to give you 6, and there are 3 of them, so that's a total of 18. So if we're going to add all of these up, we are going to have, so you'll notice here too, just to let you know, that there's not an extra electron floating around in here, right? Because this collectively, this guy's not charged, okay? So we're just going to add it up normally, okay? So we have 18 plus 5, so that's 24. So that's E half, okay? So 2, sorry. So E shared is going to be hydrogen needs 2, nitrogen needs 8, and oxygen needs 8 times 3, so that's 24. 24 and 8, 32, so it's 34 E, so that's my E need, okay? And then what we're going to do is we're going to calculate the number of bonds. So remember, the number of bonds is going to be E need minus E have. So that's 34 minus 24, which is 5 E shared. And then finally, the number of bonds is going to be, not 5. Sorry, I jumped ahead of myself. That's 10, right? And the number of bonds is going to be 10 divided by 2, which is 5 bonds. Okay, so now we're going to look at this guy, okay, and we're going to place our central atom. We'll just do that. So again, hydrogen's never the central atom. So our choice is it one of the oxygens or this one nitrogen? So it's the nitrogen. It's the nitrogen for 2 reasons. One, nitrogen is the solo atom, but also nitrogen is the least electronegative. According to our electronegativity trend, nitrogen is less electronegative than oxygen. It is more to the left of, it's to the left of oxygen on the periodic table. So we're going to place nitrogen, then I'm going to place my 3 oxygens. Okay, and then here's the key with the oxyacids. This remaining hydrogen is not going to come off of the oxygen or the nitrogen. It's going to come off of one of the hydrogens. Does it matter? No, not at this point. Okay, because technically all of these oxygens are equivalent to each other. So you can just pick one, okay? So I have my atoms placed, and I already have one of the 5 bonds placed right here, So I need to place 4 more bonds. Well, I know that obviously I'm going to have a bond between each, okay? So that's 4 total. I need 1 more. Does it matter where I put my double bond? Yes. I can't put it here, okay? Because oxygen really only likes to be bound to 2 things, okay? Since it's already bound to the nitrogen here, and then it's also bound to a hydrogen here, it doesn't want to be bound to anything else. So putting the double bond here won't work. So I'm going to put it here. Could I have put it here? Yeah, that would have been fine, but I'm gonna keep it here. Now you might be wondering, why does oxygen only like to be bound to 3 things? Well, this goes back to our orbital diagram, right? We know for oxygen, first of all, this is 1s, 2s, and 2p. Oxygen has its 1s orbital filled, and then it has 6 valence electrons. So 1, 2, 3, 4, 5. Sorry, hold on. 5, 6. Okay. So if I say, when I said oxygen likes to be bound to 2 things and no more than 2 things, that is because oxygen only has 2 vacant spots available to accept electrons. Because it only has 2 vacant spots available, when it binds to something or participates in covalent bonding, it's like, okay, I only want 2 more electrons and that's it, because that's all I have room for. Okay, so oxygen likes to be bound to generally only 2 things. If we were to look at nitrogen, for example, so this was oxygen, right? Nitrogen, for example, got the 1s, 2s, and we have 2p. Nitrogen has a filled 1s, a filled 2s, and then it has 5 valence electrons total, leaving room for, those are my little vacant boxes, leaving room for 3 more electrons. So since it has 3 more electrons, it has room for 3 more electrons, right? Ideally, nitrogen likes to be bound to 3 things, okay? Because it only has space for 3 more electrons. So that's just a little preview for organic chemistry for you guys. And this is also helpful for Lewis structures. Okay, so zooming out, we placed our 5 bonds. Okay, that got rid of 10 shared electrons. We had 24. So now we have 14 electrons to place. And what you're going to have to do now is go around and make sure that everybody has the right amount of valence electrons. Hydrogen only likes to be bound to 1 thing. It can only be bound to 1 thing. Again, that is because it only has a 1s orbital with a 1s electron in it. So it only has room for 1 more electron. So that's why it only likes to be bound to 1 thing. So hydrogen's good. This oxygen right here has 2 4 electrons associated with it. It needs a total of 8. So I'm going to give it 8. 1, 2, 3, 4. Now, so this oxygen's good. Nitrogen has plenty of electrons. It doesn't need any more. It has 8. This oxygen right here needs 6. And then this oxygen right here needs 4. Sorry. These are my little dots. Okay. So, let's see what I just placed. I just placed 4 here, so that gives me 10. I just placed 4 here, which now gives me 6, and I placed 6 here, which leaves me with 0 electrons left. So this collectively is the Lewis structure for HNO3, okay? For these oxyacids, so the take-home message for this one is it's going to be the same type of method that we've been doing before. Since there's no charge on it, we don't add an electron, okay? We don't add any unnecessary electrons here. And since we do have, it is an oxyacid, it does have a hydrogen with it. The hydrogen doesn't come off of the nitrogen, it comes off of one of the oxygens. Okay, we will do H2SO4 in lecture. So there are some exceptions to the octet rule, and I'm just going to let you know about those right now. So the Lewis theory is often correct in its predictions, but exceptions do exist. For example, NO, nitrogen oxide, which has 11 electrons, right? And this is what it looks like right here. It's impossible to write a good Lewis structure for molecules with an odd number of electrons, right? This guy right here has a single electron by itself. Usually they exist in pairs. This is called, just to let you know, this is called a radical. Right. So it's impossible to write good Lewis structures for molecules with odd number of electrons, yet some of these molecules exist in nature still. All right, so this is a stable radical. In such cases, we write the best Lewis structure that we possibly can. All right, so there's nothing that we can do. This nitrogen is going to have 1 electron unpaired. Why didn't we give it to the oxygen, that unpaired electron right here? Well, oxygen is more electronegative than nitrogen. Since it's more electronegative than nitrogen, oxygen is going to pull electron density closer to it. It's also not going to share any unnecessary, or have any unnecessary sharing of electrons, right? It's only going to share the electrons that are in these two, this double bond. It's going to have a full valence. Nitrogen is less electronegative, so it's going to have to settle with having that 1 single electron. Another significant exception to the octet rule is boron, okay, which tends to form compounds with only 6 electrons rather than 8. So boron is, so again, there are compounds that have compounds themselves that have that are exceptions, and then there are elements that have exceptions. Boron is one, hydrogen is also one, okay? Boron likes to have 6 electrons associated with it. Hydrogen only likes to have 2, right? And so because boron likes to only form, or likes to only have 6 electrons associated with it, BH3 and BF3 are examples of which are compounds that exist in nature. And you'll see here that boron only has, in BH3, it only has 6 electrons associated with it, but it's completely content with that. Other exceptions to the octet rule are anything sorry. Okay, so we'll say any element that is greater than n equals 3. So if it's in the n equals 3 or greater principal quantum number, remember, even though it might not necessarily have electrons in a d orbital, it still has access to a d orbital because it's in an n equals 3 or greater. And most of the time it's access to an empty d orbital or d subshell. So sulfur and phosphorus are such examples because they have access to that empty 3D orbital, or say 3D subshell. it can have more than 8 electrons associated with it. Because it can have more than 8 electrons associated with it, it can bond to more than 4 things. So you'll see here, right, SF6, sulfur has 6 bonds associated with it, right? 2, 4, 6, 8, 10, 12 electrons for sulfur. Okay, fluorine only has 8 associated with it because it is in the n equals 2 shell. It does not have access to the empty 3D orbitals or subshell. Phosphorus, same thing, right? Phosphorus is in the n equals 3 as well, so it has access to these empty 3D orbitals. So it can accommodate more electrons, more than 8 electrons. These are called expanded octets. Beyond mentioning them, we do not cover expanded octets in this lecture class. You guys will cover them in Chem 200. So in spite of these exceptions, Lewis theory remains a powerful and simple way to understand chemical bonding. And like I said, we'll do lots of examples tomorrow in our lecture class. Another thing that I wanted to mention to you guys is this thing called resonance. All right, this is resonance within Lewis structures. So molecules with a double bond may have resonance structures. Right? They may have this thing called a resonance structure, and I've already introduced it to you slightly. Resonance structures are 2 or more equivalent ways of drawing a Lewis structure. SO2 was an example that I gave you guys before. Because you can put the double bond on the left or on the right, this means that SO2 has resonance, and because it can be put here, the double bond here, or it can be put here, these are the 2 resonance structures associated with SO2. The actual structure of the resonance molecule is actually an intermediate between the individual structures. Okay, that's what happens in real life. But if I were to ask you to draw the equivalent resonance structure, both of resonance structures of SO2, you would have to draw both of these, and you would have to represent them collectively, or you would have to connect them essentially by a double-headed arrow. Molecules with resonance structures are more stable than other molecules because their electrons are delocalized, right? So the reality is, like I said before, the actual structure isn't this one and isn't this one. This double bond right here is delocalized across the entire structure. So really, you would have this kind of like dotted line. Oops. Let me do it like this to show. Now, this isn't a correct Lewis structure, right? But what I wanted you to show is how we can essentially combine these 2 resonance structures into one structure, and that is how SO2 actually exists in nature. But when you're drawing Lewis structures, you can't draw something like this. You need to draw it like this, showing that and you need to show both resonance structures if asked, okay? And that's because the double bond can exist here or it can exist here. So again, equivalent Lewis structures for the same molecule, all right? This has to do with double bonds. This is resonance. In nature, we find that the bonds are equivalent. We can account for this in Lewis theory by representing the molecule with both structures. This is called, again, resonance, with a double-headed arrow between them. All right, so that's this guy right here. And again, this is just repeating myself. The true structure of SO2 is intermediate between these 2 resonance structures. Okay, so we learned already how to write Lewis structures, how to draw Lewis structures. Well, how does that help us predict what the molecule is going to look like? So we can take the Lewis theory and we can combine it with a new theory called VSEPR, which stands for valence shell electron pair repulsion theory. And if we combine those two theories, we can predict what the 3D structure of a molecule is going to look like. VSEPR theory is based on the idea that electron groups, okay, this is important, electron groups, which are lone pairs, single bonds, or multiple bonds, repel each other. So electron groups repel each other. Because electrons are negatively charged, and we know that negatively charged things aren't attracted to each other, they repel each other. All right? The same thing happens for electron groups, right? Double bonds, lone pairs, triple bonds, single bonds, these are all electron groups, and they will repel each other. The repulsion between the negative charges of electron groups on the central atom determines the geometry of the molecule. So, the repulsion between the negative charges of the electron groups on the central atom determines the geometry of the molecule. So if we had to predict the shape of CO2, for example, we drew the Lewis structure right here, okay? The geometry of CO2 is determined by the repulsion between the two electron groups around the central atom. The two electron groups are going to be the two double bonds. These two electron groups get as far away from each other as possible. Okay? And because there's only two things around the central atom, right? A double bond here and a double bond here. The furthest away those two double bonds can get from each other is exactly an angle of 180 degrees. So, and I'll just draw it right here, my angle, right? And this is 180 degrees. And here it is drawn down here for you, right? So these guys are going to get as far away from each other as possible. And for two electron groups, that's 180 degrees. And since it's 180 degrees, the resulting shape of CO2 is linear. It forms essentially a straight line. That is different than something like this guy right here, okay? H2CO has the Lewis structure of this. And actually, we'll draw this guy tomorrow as well. So here's the Lewis structure for it. This molecule has 3 electron groups around the central atom. So the first electron group, remember, electron groups are double bonds, triple bonds, single bonds, and lone pairs. So if we're looking at just the central atom has, this is an electron group, this is an electron group, and that's an electron group. So that means the electron group has 3 E groups around it, okay? These 3 electron groups get as far away from each other as possible. So since there are 3 things around it, that results in bond angles of, which is, 3 things around it, right? This is my circle, 360 degrees. We divide it by 3, we're going to get 120, right? This is 120, right? Resulting in a bond angle of 120 degrees and a 3D geometry called trigonal planar. So this is the second 3D geometry that we've learned. And this is what it looks like. Trigonal planar. Okay? If we were to rotate and turn this molecule on its side, it would be flat like a sheet of paper. Okay? And this shape results from the 3 electron groups bound to the central carbon atom. So far we've learned linear and we've learned trigonal planar. These angles predicted for H2CO are approximate, okay? So this isn't exact, it's just approximate. The CO double bond contains more electron density than the CH single bonds. So it essentially means that the CO double bonds wants more room because it has more electron density associated with it. So it's going to push, it's going to push this down a little bit more, okay? Closing this gap ever so slightly. But you'll talk about that more in Chem 200, okay? But essentially that would result in these bonds being roughly a little bit more than 120. And then this bond right here would be a little bit less than 120. It's going to be pushing, because it's this double bond right here is pushing these bonds down. It wants more room, right? And it wants the most amount of room it can get. But again, like I said, these are, this is approximate, right? So this bond up here would end up being, what was that, 122 bond angle. And this bond right here was about 116 degrees, okay? And that results from this double bond, right? Wanting more room, so pushing and closing this bond a little bit further. Or I should say this bond angle. So for this class specifically, I'm not going to ask you to memorize 116 and 122 for this particular structure. It's just really important for you to understand that linear is 180 degrees, trigonal planar is 120. Okay? So for this class, it's important for you to understand that trigonal planar geometry has 120 degree bond angles, and linear has 180. So what about something like methane, right? Predicting the shape of methane. We already went through the Lewis structure of methane, right? And this is what it looks like right here. And so the first thing you're going to have to do is look at the fact that this central carbon atom has four electron groups, okay? 4 single bonds. So we can no longer look at the molecule as a flat, like disc shape, okay? Because again, the electron groups repel each other. So they're going to arrange themselves around the central atom in such a way where they have the most amount of room possible, okay? This results for 4 electron groups around the central atom. This results in a shape called tetrahedral, all right? Tetrahedral. And the bond angles for tetrahedral are 109.5. A tetrahedron is a geometric shape with 4 triangular faces. So this is kind of what it looks like. In a way, you can think about it like it's a, well, the way that they have this set up, this looks kind of like a pyramid. Right? With the central atoms right here. It's kind of ugly. But the big take-home message is that each bond angle is 109.5 degrees. CH4 is shown here with both. This is a ball and stick model. And then, I'm sorry, yeah, and then there's I think I removed the space-filling model. So this is like I said, this is a really good, space-filling is fine too, whichever. Either way, this is a really good example of, you can see how the carbon atom is in the center, and you can see how each hydrogen atom is oriented around it in such a way that it has the most amount of room possible, and specifically 109.5 degrees. This is the space-filling model right here. The ball and stick model is not much nicer to see the specific bond angles, but here's what it would actually look like. And again, this is still 109.5. So the mutual repulsion of the 4 electron groups causes the tetrahedral shape. The tetrahedron allows the maximum separation between the 4 groups. when we write the structure of methane on paper, it may seem that the molecule should be square. Square planar. Square planar looks, it's almost like just a square, right? Where this would be a hydrogen, 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 and this would be carbon. And it would, if we were to rotate it on its side, it would be flat, but that doesn't make any sense because the bond angles would be 190 degrees. So naturally, methane is going to adopt this this shape because 109.5 is definitely greater than 90 degrees. So it's going to develop this tetrahedron shape. In 3 dimensions, the 4 electron groups can get further away from each other by forming the tetrahedron geometry. So we're going to talk about another one really fast. This is a kind of an exception. I'm going to draw the Lewis structure really quick for methane so you can see this. Not methane, ammonia, sorry. NH3. Okay. First we're going to add up the electrons, valence, nitrogen, 5, hydrogen, each has 1 times 3, which is 3. It's a total of 8. Okay. Let's see, so that's the E have, our E need, E ned is N equals 8, hydrogen equals 2, and there are 3 of them, so that's 6. So that's going to give us a total of 14 for E need. Our E shared is going to be 14 minus 8, which is going to give us 6 shared. I don't know why I keep forgetting my... And then our number of bonds is going to be equal to 6 divided by 2, which is 3 bonds. Our central atom is nitrogen, so we're going to place our hydrogens around it. Let's move this one. And then we are going to place our 3 bonds. Since that's 3 bonds, that's 6 electrons, but we had 8 total. We have 2 more electrons to place, and the only place that they can go is on the nitrogen. Now, if we want to predict the geometry of this, what are we going to do? The first thing we have to do is count electron groups. Okay? That's the first thing that we're going to have to do when we're predicting the geometry. The electron groups, we have 3 single bonds and 1 lone pair for a total of 4 electron groups. Okay? 4 electron groups. 4 electron groups put us into the tetrahedral. Okay? Put us into the tetrahedral category for 3D shape. But it turns out this is not the 3D shape that this adopts isn't technically tetrahedral. Okay? The fact that we have a lone pair right here means that even though we're in the tetrahedral shape, it's going to have... Here, I'll jump down and just show you really fast. So if we look at only the electrons, if we look at only the electrons, or the electron geometry, the geometrical arrangement of the electron groups is tetrahedral, like I said before. But this new thing, molecular geometry, so we have electron geometry, okay? But now I'm introducing this thing called molecular geometry. The molecular geometry is the geometrical shape or the arrangement of the atoms, including the lone pair. This is called trigonal pyramidal. Okay, so even though we counted 4 electron groups, which gave us, I'll just put electron, that's going to be electron geometry. the molecular geometry is a subcategory of the electron geometry where we just look at the lone pairs. So if we have, we assign our electron geometry, right, which was tetrahedral. But then we sit back and say, okay, we know it's tetrahedral, but there is a lone pair right here. So since there's one lone pair within the tetrahedral electron geometry gives us a molecular geometry of trigonal pyramidal. Okay. This is because we can't see lone pairs. Okay, since we can't see lone pairs, this is what we end up seeing. This is what ammonia looks like. That doesn't look tetrahedral, does it? And when we look at this, it's technically not tetrahedral. It's trigonal pyramidal structure, okay? But we had to get to this name, we had to get to this category by first identifying the number of electron groups, which gave us the electron geometry of tetrahedral. And then within the electron geometry of tetrahedral, we're able to get our molecular geometry, which was trigonal pyramidal. The only reason why we got trigonal pyramidal is because anything with an electron geometry of tetrahedral with one lone pair is trigonal pyramidal. Okay? So the bond angles at NH3 are actually a few degrees smaller than the ideal tetrahedral angles, and this is because electron lone pairs repel more than anything else. Okay, so they're going to push these bond angles to be a little bit less than 109.5. All right. So let's look at another one really fast. We're going to go back and look at water really quickly, okay? So remember, we know water is this. If we count the Lewis structure for water is this guy right here. If we count if we wanted to get the electron geometry, we count E groups, okay? So remember, E groups are the two single bonds right here, this lone pair, and this lone pair. So that's a total of 4 E groups. That says groups. That's going to give us an electron geometry of tetrahedral. Okay? But because we have 2 lone pairs associated with it, okay, the structure is bent. All right, and that is because, let me see if I can just draw this a little bit better for you guys. This is so much better to teach in class. Let me just show you what I mean by this. So you're like, what are you talking about? You're saying bent, now you're saying tetrahedral. So remember, this is okay, how about this? This is a generic example, okay? This is, this is my ball and stick example of a tetrahedral. Okay, these aren't actually elements, right? We're going to fill everything in. We know that for water, the Lewis structure is this. Okay, so if we know the Lewis structure is this, what I'm going to do is I'm going to go into this. We know that, I'll take a step back really fast. This is the Lewis structure. 4 electron groups. Right? Each electron group, there's a lone pair here, and then 2. That's 1, 2, and then 3, 4. So 4 electron groups gives us tetrahedral. So that means E geometry tetrahedral. Okay? So now I'm going to take the Lewis structure and I'm going to translate it into this. So the central atom, oxygen, so I'm just going to replace that with an O, and I'm going to put the two hydrogens, let's put them, well, it doesn't really necessarily matter, but I'll put them here, and I'll put it here, okay? These are still the same bonds. Okay? Now what I'm going to do is I'm going to place my two sets of lone pairs. Now the only place that they can go is here and here. So I'm going to delete that, and I'm going to put lone pair here. I'm also going to delete this and put a lone pair here. So what you'll notice is that this no longer looks like my tetrahedral arrangement. This now gives me a molecular geometry. Okay, and that molecular geometry is bent. Why is it bent? I wish I could take this and, oh, I can. Yay. So if I take this and rotate it, what you'll notice here is that looks like, it's kind of a messed up example, but here, I'll do this now. Right? That's my water molecule. My water molecule looks like it's bent. Okay? So we had to first count our electron groups to get in our tetrahedral arrangement, then go back and evaluate the number of lone pairs within the tetrahedral arrangement to get the molecular geometry of bent. And turns out this is exactly what water looks like. If we were just to call it tetrahedral, it would not be an accurate representation, okay? Tetrahedral is its electron geometry, but its molecular geometry, the way that it actually looks in real life, because remember, we can't see lone pairs. So the way that it actually looks, it's going to look like this bent structure, okay? That's because the two lone pairs take up two coordination spheres, or coordination environments, of the tetrahedral electron geometry environment. Let me go back and just show you really quickly with nitrogen, or with the ammonia as well. So remember, we have ammonia. I already drew the Lewis structure. We knew it was look like this. If we were to count, make this a little bit smaller. If we count the electron, if we count the electron groups, right? The electron groups are going to be this bond. So 1, 2, 3, 4. So that's 4 electron groups, which gives us tetrahedral electron geometry. Okay, so again, I'm going to draw that generic really fast. So tetrahedral electron geometry. Right? Each with a bond angle of, just to let you know, remember, 109.5 degrees to start off with. Now I'm going to place my atoms in this. So we know nitrogen. I'm going to do it a little bit bigger too. Nitrogen is going to go in the center. All right. Hydrogen atoms are going to go here, here. This is what I was talking about coordination spheres, right? So the hydrogens are all going to go right there, and then the lone pair is going to go right here. Okay. So, and I'm just going to go ahead and I'm going to, if I can, So what you see here is that even though we are in the tetrahedral electron geometry, this does not look like tetrahedral. This looks like, if you were to look at it, the actual structure of ammonia looks like this, right? The ball and stick structure. This is what it looks like in real life, where we just see 3 hydrogens around a nitrogen. This is called trigonal pyramidal. All right? So even though we have 4 electron groups, which give us a tetrahedral electron geometry, the molecular geometry is trigonal pyramidal because of 1 lone pair. Okay, so in real life, it's going to look, nitrogen's in the center, right, and we have this kind of triangular shape, right? And because lone pairs, repel the most, they're going to push these bond angles down, squeeze these bond angles, right? So the overall bond angle is going to be a little bit less than 109.5. Okay? And that actually goes the same for water as well. Okay, so this is a nice little table explaining the shapes, explaining the shapes of molecules and how you can predict them. Okay, so you'll notice here if we have 2 electron groups, okay, that's going to give us a linear geometry, electron geometry of linear. The bond angles are 180 degrees, and because there's only 2 electron groups total, there can't necessarily be any lone pairs. And if there are, it'll still be linear. So the molecular geometry is going to be linear as well. If we have 3 electron groups, okay, that's trigonal planar. Bonding angles at 120. If there are all 3 of those electron groups, if all 3 of those are bonds, then the molecular geometry is going to be trigonal planar as well. And this is the example right here. But if 2 of those bonding groups or electron groups are bonding groups, and 1 of them is a lone pair, even though the trigonal planar we're still in the trigonal planar electron geometry, we're going to now have a molecular geometry of bent. And again, that's because we have 1 lone pair associated with it. SO2 is an example, right? SO2, sulfur dioxide, when we draw the Lewis structure here, and we look and we evaluate it, we know that because it has 3 electron groups associated with it, it's going to be in the electron geometry of trigonal planar. But since 1 of those electron groups is a lone pair, as you can see right here, it is going to be a molecular geometry of bent. So its actual 3D structure in real life is bent. Now we're going to jump up to 4 electron groups. Okay, so that these next 3 are all 4 electron groups. 4 electron groups are all tetrahedral in terms of electron geometry. 4 electron groups, tetrahedral, 4 electron geometry. If all 4 of those electron groups are bonding groups, like methane, 1, 2, 3, 4, methane is going to have a molecular geometry of tetrahedral. But if you have an example where you're in a tetrahedral electron geometry, but 1 of those bonding groups is a lone pair, as you can see here, then we no longer have a tetrahedral molecular geometry like we did in methane. Now we have trigonal pyramidal, right? 1, 2, 3 bonding groups and 1 lone pair. And that's what this looks like. Trigonal pyramidal. Zoom back out again. If we have, instead of out of the 4 electron groups, if 2 of them are lone pairs, even though we're in a tetrahedral electron geometry, we're going to have a bent molecular geometry, right? Like we did for water, like it is true for water, right? Because that is still, it's 4 electron groups, 1, 2, 3, 4, but since 2 of those electron groups are lone pair, we now have a bent structure. So this is also, and I kind of organized it a little bit in another way so you guys can see it. So again, predicting the shapes of molecules. So for example, linear, there are 2 electron groups, 0 lone pairs, you're always going to have linear for 2 electron groups. Again, this is around the central atom. If you have 3 electron groups around the central atom, you are going to be in the electron geometry of trigonal planar. Okay, so just go ahead and say really fast. Purple, everything in the purple is electron geometry. Okay, everything in the red is a subset, a subcategory of electron geometry, and that's the molecular. If there are no lone pairs around the central atom, the molecular geometry is going to equal the molecular geometry, and the molecular geometry are the same. Okay, so if we have 3 electron groups, that puts us in a trigonal planar electron geometry. If we have no lone pair, then the molecular geometry is trigonal planar. If we have 1 lone pair, then we have a bent molecular geometry. Jumping down, or I should say up to the 4 electron groups, that's a tetrahedral electron geometry. If we have 0 lone pair, that is a trigonal planar molecular geometry. That's a mess. I'm sorry. That is a total typo. It's not trigonal planar. It's tetrahedral. Okay. So if we have 0 lone pair, we have a tetrahedral molecular geometry. If we have one lone pair, we have a trigonal pyramidal molecular geometry. And if we have 2 lone pair, we have a bent molecular geometry. All right, so recap really fast. We used VSEPR, right? Valence electron repulsion theory, valence shell electron repulsion theory to predict the shape of molecules. We started off with the correct Lewis structure. Then we determined the total number of electron groups around the central atom. This is the electron geometry. Then we reevaluated the electron geometry further by determining the molecular geometry. All right? If there are no lone pairs, then the molecular geometry. If there are no lone pairs around the central atom, then the electron geometry is the molecular geometry. If there are lone pairs, the number of lone pairs determine the molecular geometry. Okay? You will be given a chart. You won't have to necessarily memorize all of this, but you need to know how to appropriately predict the molecular geometry of a compound by drawing the Lewis structure and then placing it into the appropriate category by first counting the electron groups, then evaluating whether or not the electron group, any of those electron groups are lone pairs. So again, this something like table 10 will be given to you on the exam. It is important to note really fast that the molecular geometry is the 3D shape of the molecule. Is the 3D shape, okay? And in our next lecture, we're going to look at, now that we can predict the 3D shapes of molecules, now we're going to look at how the 3D shape affects the certain properties and thus the chemistry of the molecule. And for that, we're going to stop here.